Welcome to the Astrophysics Podcast. All right, let me start by telling you a story about Einstein. Back in 1915, when he first published and promoted his general theory of relativity, he predicted that light should be attracted by gravity. In other words, the path of a light ray should be bent or curved in the presence of a gravitational field, according to Einstein. Specifically, he computed that starlight should be deflected a very small amount when passing by the gravitational field of our sun. In principle, it should be possible to see this effect because it would change the apparent position of stars whose light passed nearby the sun. But in fact, this is a very subtle effect that can only be measured during a solar eclipse. So, in 1919, the astronomer Sir Arthur Eddington actually measured this exact effect during an eclipse, showing that light was attracted by gravity in exactly the way Einstein predicted, which is why we call it the theory of relativity and not the belief of relativity. You might notice that we also don't call it the fact of relativity. This is because, as a good scientific theory, it always has the possibility of being disproven by some new experiment. So when a theory that could always be disproven but isn't disproven and it stands the test of time, it gives us more and more confidence that it is an accurate description of reality. But of course, there is no way to prove a theory true. It can only fail to be disproven. And that's how the scientific method works. In astrophysics, however, research doesn't always proceed in a perfect, orderly manner of hypothesis to prediction to experiment. The reason for this is, in astrophysics, we are constantly discovering new phenomena that we never expected to see. It seems as though every time we come up with a new way of observing the universe, we discover new astrophysical objects and events that we hadn't predicted at all. So, as a result, observers usually lead the way, while theorists usually spend most of our time trying to explain things we already seen, never mind predicting new things that we haven't even seen yet. And this brings me to my guest today. I am very happy to be joined by Professor Abigail Polin from the Department of Physics and Astronomy at Purdue University. One of Professor Polin's most impactful contributions is something I think is pretty unique in astrophysics. Dr. Polin actually predicted a new type of supernova. That is to say, she calculated that if you were to explode a white dwarf star in a very particular way, it would look very different from any supernova that we had ever seen before. And then, just 1 year later, astronomers discovered a supernova that matched her predictions precisely. We're going to talk with Dr. Polin about how stars explode, how she calculates what a supernova will look like, and how she decided to become a scientist in the first place. I'm Paul Duffel, and this is the Astrophysics Podcast. By the way, I'll give you a fake intro.
All right, and then you're going to do a real one later.
I do a real one in post. It'll be really good. I know what I'm going to say. I'm going to talk about how genius you are and compare you to Einstein and everything.
Please don't do that.
Okay. We'll see. Are you ready?
Probably.
Okay. Welcome to the Astrophysics Podcast. I'm Paul Duffel, and my guest today is Dr. Abigail Polin, Professor of Physics and Astronomy at Purdue University. Dr. Polin, thank you for being on the program.
Thank you for having me.
I'd like to start things off by talking about you personally and how you got to be a scientist before we get into the actual science. So let's start by telling me a little bit about where you grew up.
Yeah. So I'm from Lancaster, Pennsylvania. It's a pretty rural area, about an hour from Philadelphia. I grew up on a small farm.
Wow.
Yeah.
So that's not what I think most listeners were expecting when they had an astrophysicist on, that they grew up on a farm.
It was a small farm,
okay.
Mostly a hobby farm. We had goats, a lot of goats, so many goats, chickens, geese. At one point, we even adopted a runaway pig. So
wow. So then, and you were in, that's of course Lancaster, Pennsylvania. That's Amish country.
it is. It was an Amish pig.
It was an Amish pig, but the rest of the family was not Amish.
No. We like to joke that was the smartest pig ever because it found the only Jewish farmers in Lancaster County. So we didn't eat it.
So it ended up being a pet. That's nice. So that's great. So you grew up on a farm. So you're out on the farm, and somehow that goes from that to wanting to study astrophysics eventually at some point in your life. So do you have a memory of the first time you knew you wanted to do science or physics or astronomy?
So I was always a curious kid. I always really liked math. And I think it took me until later than a lot of my peers to realize, physics is kind of the point of all that math I've always really liked. It's like math is the language to understanding how the universe works.
I had the same. I don't know exactly what point I had that moment. I guess it was like high school. And I realizing that was what I wanted. Like realizing that was what physics was. Like I heard the word physics, but I didn't really know what it meant.
Yeah, my first physics class, we didn't even really call it physics. We called it general science. It was the first science class you took in high school, and it happened to be that it was mostly physics, and it was algebraic physics, but it was, math can explain how things move or how gravity works. It was very cool for me to kind of put it all together.
It's empowering in a way. Like you get to be like, I can figure out how all these things that are in the world are working.
Right, and that kind of interest can take you for a really long time going, all I have to do is learn how to do the math, and I can understand how anything works. And then it turns out there is a degree to which our fields are complete.
Sure.
Yeah.
So yes, like any science, there's always some edge to how far we've gotten it, and there's some things we
eventually
don't know what the mathematics we need to explain.
Exactly. Eventually, our work comes less like a homework problem with an answer, and a lot more like figuring out the math needed to explain something.
It is an amazing thing, like that how physics works, and realizing that moment. And I remember having that same moment myself. But so that's when you wanted to do physics. But what about astronomy? That's astrophysics.
So I had been interested in space, like many kids, from a very young age. Where I grew up going on vacation near family in North Carolina. We were lucky enough that at the time, anyways, the Outer Banks, these little sandbar islands off the coast of North Carolina, had so little light pollution that you could see the Milky Way, and that blew my mind. I remember sitting outside with my dad, who's an avid photographer. He was taking pictures of the moon. I'm just staring at the sky.
Wow.
And so I was always, I think, interested in space. I also grew up with a lot of societal pressures making me feel like maybe I wasn't supposed to be as interested in those things. But then when I actually started studying physics seriously, I realized space was kind of a place where I didn't have to choose a type of physics. I could do a little bit.
Astrophysics is kind of the best that way.
Yeah.
It's a little bit of everything.
Yeah, you get to do a little fluids, a little quantum.
Nuclear physics. Is everything. All that stuff happens out in space.
Yep.
I love that aspect of it too. So you mentioned your dad. Were your parents big influences on how you became to be a scientist?
I think so. Both of my parents are very into science. They're both very creative people. My dad's a doctor, so obviously that's a little bit STEM-minded right there. But they both really love science, and they were both very encouraging in that manner, even when... or maybe even especially when, like, all the things were telling me I wasn't supposed to do this. So I remember one summer, I think it was maybe a transition year between middle school and high school, or maybe right before middle school, I can't really recall. My mom found out that our local science museum, the North Museum, was doing these science day camps. And she came to me really excited. She's like, I think you should do this. You'd love it. And I crossed my arms and I stomped my feet and I said, no, Mom, there becomes an age where girls just don't do science anymore.
Oh, my. Oh, no.
And my mom is a great mom and said, oh, no, not my daughter. And signed me up for every science day camp that museum had all summer.
Oh, wow. Wow. So she went the other direction.
Yeah.
So she was pushing back on the societal pressures.
Absolutely.
Well, that's great. It's good that, that's good they were so supportive, even even when you weren't supportive of yourself.
Exactly.
That's amazing. And so that's great that you had this supportive parents. Do you think the experiences you had when you were younger drove you toward astrophysics?
I think I found astrophysics personally through a series of trying things as a college student, trying different fields of physics and choosing what the combination of what I thought were the most exciting problems and also what I liked doing on a daily basis.
Okay, so then maybe we'll start with how did you eventually decide on physics? I guess you came to astrophysics eventually in college, but when did you decide on physics?
I think really that first physics class I took in ninth grade in high school. Yeah,
Wow.
I always had it in my head. The teacher of that class was named Mr. Way, and at the end of the year, he dared us all to continue. He dared us to take AP Physics. He said it would be the hardest class we'd ever take in our life, and that turned out not to be so true.
Well, teachers say that sort of thing sometimes.
Well, yeah, especially if you move on to the physics that's harder than AP Physics.
Right.
But he dared us all, and I think at that point it kind of stuck in my head of, you've really enjoyed this year, you've really enjoyed this way of thinking and problem solving. You should do that. I at that point had it in my head of, that was the beginning of my trajectory of, I kind of want to try this until I can't anymore. I think we call that imposter syndrome now. But, I had forever after that trajectory of, I will do this until I fail out.
Oh, wow. Well, what you said before about, the idea that physics, other people, it's treated as like, this is the hardest science, the most difficult science for everyone. And for some people it is. And for a lot of people it is. But
I think that's very personal.
Yeah.
I think we get that reputation because we're very mathy, and math is or is not for people very polarizingly. Mm-hmm. But I don't think physics is harder than any other field you have to put this amount of work into.
No.
Right.
I think, in my experience when I was in high school, I found physics to be, to me, easier than like chemistry or biology.
Right.
Because that I felt like it made sense. If once I had a handle on all the math, I could.
Right. And I think that's because you and I think in a way that's conducive to becoming a physicist, whereas it was just as likely we'd think in a way that's conducive to becoming a biochemist.
Yeah, exactly. So, because physics is a sort of pattern of thought, and once you get used to that pattern of thought, everything becomes much clearer.
Right. It really is like learning a new language of once you learn how to speak the language, you've kind of overcome this barrier and you have the tools to keep going and keep learning.
Okay, so if you got interested in physics in high school, then somehow in college you got interested in astrophysics.
Yeah, and that was through a series of research projects. I actually didn't start in astrophysics. I started in soft matter physics, studying granular materials.
All right, you're going to have to explain what soft matter physics means.
Yeah. Well, soft matter is matter that's not so hard.
Matter that's soft.
But
that's not a bad description, by the way.
It's not very useful.
Things that are not solids, not liquids.
Right. For me, that meant grains, so like sand.
Okay.
Yeah. And I started, my first research project was in understanding how granular materials moved when we do things like shake them or shear them back and forth. And how, if you imagine you could take a microscope and look at the shape of all your little particles of sand, how the geometry of that shape affected that kind of movement.
Okay, that's very interesting. So I mean, I love this. I love this science too. It's not astrophysics, but I love that idea. Like, how we have, equations describing how solids behave, and we have equations to describe how liquids behave. We don't really have good equations to describe how something like sand behaves,
Right.
which is kind of incredible.
Well,
you know?
the whole field started because I believe it was Reynolds was trying to understand fluid flow, and he made a model using essentially marbles. Mm-hmm. And found that, this doesn't behave like a fluid at all, like not even qualitatively, because grains do something called dilation that fluids don't. So basically there's friction in between each granular particle. That means when we try to put forces on them, they tend to expand instead of contract.
Okay.
So you can see this if you picture yourself walking along the beach on that damp sand that, waves have just walked over. Mm-hmm. You'll notice the footprints you leave behind are dry. And,
oh, wow.
Right. And that's because when you step on that sand, you're exerting a force, and the friction between the granular particles are causing that sand to expand.
That's incredible.
Yeah, so the water's going down and filling the space in between the grains and leaving a dry footprint.
That's so funny. It's one of those things that you see like all the time and don't even think about.
Right, exactly.
That's how physics is, right?
Yep.
There's explanations for these things sometimes.
And for me, that was a great way of getting started because for an undergrad, it was a tabletop experiment. It was really fun. It was something that I could understand all parts of while still needing to learn some of the fundamentals of perhaps why things behave like this.
Right.
Right. I could study cause and effect pretty easily.
Right.
Right. And it was a blast. But I also learned that I probably didn't want to be spending my daily life in a laboratory in that kind of setting.
Oh, really?
Yeah. It was fun, but it wasn't the thing that motivated me.
Okay.
So from that point, I tried a number of different other undergraduate research projects that stretched anywhere from like a year through to a summer to try to figure out what I liked doing with my everyday.
Yeah.
Yeah.
And then eventually what you landed on astrophysics as the thing that...
Well, I landed on computer coding, honestly, of simulations.
As the thing that day-to-day you could do.
That day-to-day I liked doing. And astrophysics were, I think, the coolest problems I could find to solve with that kind of day-to-day.
Okay, so is that when you felt like, when did you really feel like you started to learn how to be a scientist? Like
throughout that process of learning what research is like.
Okay, so that would have been, as an undergrad, trying different things out.
Yeah.
Okay.
And obviously I still had far more to learn. Some of the things I thought of how the world worked doesn't actually work that way.
Yeah.
It's an entire process, and I'm sure I'm still learning today.
I don't feel like I learned how to be a scientist until about my third year of grad school. I started to realize there's a way of...
Is it through the same process, though? Was it because that's when you were really heavily getting involved in the day-to-day of research instead of the coursework?
Yes, absolutely. I mean, that's exactly right. Because the coursework, it's not really about... Coursework isn't really science, exactly, because you're not going through the process of... figuring out how to set up the problem that will answer your question.
It's more a 4 to 8 year process of learning the tools you need to understand those inquiries.
Yeah, it is interesting how that is. With coursework, we spend all this time teaching coursework, which is, obviously important background material for students to learn, but it's not science, really. You're not teaching them, the scientific method, really. We try to have labs and stuff for that, but even that is hard because we've set up the lab. We already told them how they get the answer.
Right. Anytime that we fundamentally already know what the answer is not actually replicating the day-to-day of what scientists do.
Right. Yeah. Right. Exactly. That's very interesting. So you're saying you learned how to be a scientist by trying out different projects like this, like the soft matter.
Right. I jumped from soft matter into the next thing I tried was kind of a data-based project on gravitational waves, working with the pulsar timing array. And then,
that, you must have enjoyed that to some extent,
well,
since
yes.
since that's astrophysics.
Yes, that set the trajectory into, I find these astronomy problems more interesting. Actually, I was really, really obsessed with gravitational waves there for a couple of years. So I did a project with pulsar timing. I did a project with LIGO while we were building advanced LIGO in Louisiana.
Oh, this is before we actually detected anything
Correct.
with it.
Both of these were before we'd ever detected a gravitational wave.
And now both of those have success.
Yeah.
All thanks to you as a grad student, I'm sure.
No, but it is really cool to see how quickly these things change,
yes,
right?
That
these things that when I was publishing my first papers, referees were saying are fiction.
Right. This is all fantasy. We won't. Who knows if we'll see this in our lifetime?
Right. Exactly.
Okay. Well. So all right. So I didn't want to get into gravitational waves and things. I know that's a whole different.
I can say
field.
One more thing if I could.
Yeah.
I think the important thing was through that process, I finally landed on astrophysics by deciding, I'm far more interested about the things creating these gravitational waves than I am in being a person who has to be the one to detect them.
Right. So in other words, that pointed you in the direction of theory rather than experiment or observation.
Yes, absolutely.
Okay. So that's how you sort of decided theory was the thing you were interested in. So we can skip ahead past all of the postdocs and everything. But now you're an astrophysicist.
Sure.
And so what are some of the things that you like the most about your job?
Yeah, well, I still feel like I'm figuring that out. So I just started a faculty position, which you kind of feel like is the end of the trajectory in some ways, but I still very much feel like I'm just starting.
Right. That's right, yeah.
But several things motivate me. Obviously, the science motivates me, especially when it can get exciting. And for me, that feels like when theory interfaces with what's actually happening in the real world. But on a more day-to-day basis, what motivates me is the people. I love talking about science with people. I love getting to help the next generations of scientists feel that same kind of excitement and build that same toolbox.
So when you say people, you mean it's a sort of cross between, some of the people stuff is going to conferences and talking to other scientists about research and what they're doing and keeping up with people, having a network of a community. Right. But then what you were just saying, also separately, being an advisor, a teacher, mentor of students.
Being able to teach reminds me of those years when you're just sitting in the classroom for the first time realizing this all is cool, right?
Yes, yeah, that's right. You get to relive that again.
Yeah, I was lucky to have really great teachers in college, and I really hope to be able to be that for students now.
Yeah.
Yeah.
So is there anything you don't like about your job?
No one likes debugging.
No, of course. Yeah, some days that's how it goes, right? I know that for sure. But anything else like?
So my field in particular, I think, can get very competitive in ways that I don't think are necessarily actually needed.
Right.
And that can be trying. That can be really hard.
We're all in the same boat. We're all trying to do the same thing. We're trying to figure out what these things are going on out in space.
But I've never understood this need that, only the first person to do it is worth... If you can't be first, it's not worth doing.
Right. And especially if you're working on explosive things like supernovae, things that are only in the sky for a short period of time.
We're all racing to be the first to understand something that's visible for a very short amount of time.
Right. So that sort of creates a competitiveness.
Yeah. It can, yes. I think there's a lot of us who are devoted to trying to turn things to being more collaborative, especially in this era where we're discovering so many transients, even per night.
Right.
That there is no one person who can do it all.
Right.
We do need to communicate with each other more.
There's nothing wrong with a little healthy competition.
Right.
But,
it's just when it goes to the extreme that it can be
Yes.
hard.
Yeah. There's no, and sometimes you just get, I understand it can be exhausting being in an argument with someone who is much more willing to argue about this for a much longer period of time than you are. That can be an unpleasant part of the job. I mean, partly why, we're all here because we're excited about it. And so we push hard and sometimes that ends up creating that. Yeah. So what would you say, this is very similar to what I've asked already, but would you say there's anything that motivates you, like what motivates you the most in your professional life? Like what gives you the energy to work on these hard problems, gets you out of bed and,
Well, we're in a really exciting time for what I do. I think we're going to talk more in detail about what I do later.
Yes. Yeah, don't worry.
But surface level, I work on supernovae, and we're in an era where we're discovering more than we ever have before, and we're about to see new telescopes. For example, the Vera Rubin Observatory is about to come online. And we're going to go from seeing possibly like 10,000 supernovae to 1 million per year.
Right.
So it's a really exciting time to do what I do because we are discovering so many supernovae, so many things we'd never dreamed of. And it's just this giant pool of information that we have to work with. As a theorist, I have so many questions arising every day that I couldn't possibly answer them all.
When you meet like a new grad student or a fellow scientist and they ask you what you work on, what do you tell them?
I tell them that I am a transient theorist.
Okay, so transient theorist. So transient meaning what?
Meaning things that happen for a short amount of time.
Okay.
So the most common one you'd think of is a supernova.
Okay, so but there are other types of transients like gamma ray bursts and tidal disruption events and things. But
FRBs, etc.
Yeah. But for our listeners, there are at least two of whom exist. My parents are definitely listening.
Again.
We'll see how.
4, my parents as well.
Okay. At least in this episode, we'll have 4 listeners.
Yep.
But in any case, for the listeners, so you can think of supernovae when you think transient.
Right.
But
what I mean by that is just something that's visible for a short amount of time.
Okay. And theorist, meaning that what? How would you define theorist?
I try to study the sources of these from a fundamental physics perspective. And normally that would look like modeling these events instead of observing them in the sky.
Okay, so you have, in astrophysics, we have theorists and we have observers, mainly. And the observers see the thing. They look through the telescope and then they see the event going off and they take data. And then theorists are, basically explaining the data or building models that, or make a prediction, hopefully.
Hopefully, sometimes.
Okay, so then what does your research look like? What is the sort of day-to-day tasks that are involved?
Right.
You mentioned debugging.
Yes, unfortunately, a lot of debugging. So what I do is very coding heavy. I run simulations of astrophysical explosions. Both, this kind of works in 2 steps. So we can run a simulation of what a supernova would look like and get a model that tells you this properties of the exploded stars, things like the velocity and temperature and composition of the ejecta.
All right, let's slow down a minute.
Yeah.
So when you say simulation, you mean you have a computer code that
I've tried to teach some laws of physics too.
Okay, so the computer program will have a bunch of laws of physics in it, and you will tell it set up some initial setup, and you like a star that explodes, and and
I ask how would the consequences of this ignition evolve.
Okay, so you blow up the star on the computer, not in real life. You do it on the computer, but then you then you see what the consequences are. How fast you said the velocity. You mentioned the velocity, how fast it moves.
Temperature, what composition it is, so what elements it's made out of.
Oh, okay, sure.
And then I do a second thing as well, and I think this is the bigger motivation, or what allows me to make a lot of progress, is I do something called radiative transport modeling.
Okay, radiative transport modeling.
Right. And so that's taking the end state of one of those computer simulations, our theory of what we think an explosion would look like.
Okay, go on.
And
don't worry, I'm gonna explain all this. We're gonna go back over this in a second.
So we take the theory and we use a number of other simulated physical properties to translate that theory into what it would look like if we saw it through one of our telescopes.
Okay, so what you're saying, let's clarify it for a second, backing up and digging into it. We have you have basically, it's a two-stage process. One stage is blow up the star using the physics of explosions, of fluid dynamics.
Exactly.
And you watch what happens, what that exploded thing looks like. But that's not what it looks like to...
Right, because we can't go stand next to a star that exploded and measure how hot it is.
Nor do we want to.
No, probably not.
I mean, it would be exciting for very briefly, but yeah. So you instead of what an observer
what
would
we
see.
observe is the photons that are released from that explosion that go through a bunch of physical properties, like being absorbed and re-emitted by different chemical elements on their way to us.
So in other words, when they look into a telescope, they see this light, this flash of light, or this brightening of light.
Exactly.
And it's this point of light on the sky, and what can we learn from that?
Right.
And so the only way we can learn something is if we build an extra model that tells us what the light would look like.
Precisely. And so in this way, we can actually say what features of these supernovae what these observed features are, what that means for what's out there, those hot balls of gas.
Okay, so it's obviously a lot of physics involved there, and in order to do both of these stages, and in order to understand how light, propagates through a star, and then all the way to a telescope, and understanding, how to relate that to the physical properties of the explosion. That's obviously a lot going on, but so then the day-to-day tasks involve, I guess, a lot of just running your code and
a lot of coding, a lot of running the code, and then and this was surprising to me, at least while starting out, large amount of data analysis. Even though my data is simulated data, there's just a lot of data statistics that you perform to understand the results of your simulated experiment.
That's that's right. That's the big piece that's extremely important, is being able to make sense of it. It's all well and good to just explode a star and say, look, this happened.
Right. It makes a really, really cool looking picture, but we want to be able to understand it.
Right. And even better is if you can figure out how to set up the problem from the beginning, that you will get some results that will be useful.
Yes, absolutely. I actually think that simulations, for me, I set them up like experiments. And maybe this is going back to my first dipping my toes into physics was a tabletop experiment. But I set up simulations very much like I have this parameter space of independent variables where I change one thing at a time and ask what is the effect of changing that one thing at a time.
Right. You have your own knob. In the universe we don't necessarily have that knob, but you do.
But I do.
Because you're making this simulation on the computer, so you have this knob that you're allowed to change.
Right. So just asking very simply, like, for example, if I change the mass of the star that's exploding by a little bit, how does that change the features we get to observe?
Right. So that's very powerful, because you can't do that in it. You can't just say, well, back that supernova up again and just do a little bit more massive star.
Right.
You can't do that in as an observer.
Right, exactly.
But you can do that sort of thing if you simulate it on the computer.
And hopefully that will allow us to take our observations and work backwards and understand, say, again, what the mass of that star that exploded was.
Right. If you do a whole bunch of different explosions with different masses, then maybe you may be able to relate the two together.
Precisely.
What would you say was your most impactful contribution? What work are you most proud of in your professional career?
During my PhD thesis, we made a prediction of what a really specific type of supernova would look like. And at the time, that type of supernova was entirely theory. We didn't know whether or not they happened in the real world.
So there was a type of supernova that you predicted, Sorry, explain this again.
Right.
You made a prediction for a particular type of supernova.
Exactly. So we made a prediction of what it would look like if a white dwarf exploded through the aid of a very thick accreted helium shell, if you want to get more specific.
All right. So we'll have to define a few terms. So what is a white dwarf, first of all?
A white dwarf is the cold, dead core of a star. We like to call them stars, but they're not really.
They're not really stars.
They're the leftover insides of stars as we actually think of them if you think of the sun. So when the sun dies, it will leave behind a white dwarf that, because it doesn't have a binary companion, will just sit there cooling off forever.
Okay, so it's not. So the sun won't explode at the end of its life, and instead it will sort of leave behind this white dwarf star.
Right.
That's just sitting there. So what's the difference? What's the difference between the white dwarf and what the sun is now?
Well, stars like the sun support themselves through fusion at their cores. So something has to keep a star up, right? Gravity is pulling all of that gas towards the center. Something has to be pushing back against it so the whole thing doesn't just squish down and collapse.
Right.
For normal stars, that's fusion. So taking hydrogen and then burning it to helium into carbon into oxygen. That process gives back some pressure that fights against gravity.
Okay, so nuclear fusion creates, makes it hot in the core of the deep in the interior of the star, and that heat provides pressure support that keeps the star alive. But with a white dwarf, that's not true.
With a white dwarf, that's not true. There's no longer any fusing going on. That part of the star's life is over. There's nothing to fuse. Well, that part of the star's life is over.
There's no more fusion going on.
No more fusion going on.
It's used up basically the fuel that it would have used to fuse.
And so it leaves behind this ball of, normally the ones I think about are a mix of carbon and oxygen, but they can also come in helium or oxygen, magnesium flavors.
And it depends on what star it came from originally,
Exactly.
whether it was whether it got hot enough to fuse helium into carbon or something like that.
Exactly. But at this point, what's common in all of these white dwarfs is there's no more fusion going on, so you need something else to support pressure, or to give pressure that fights off gravity. And what happens is, because we're not fusing, these cores become really, really compact.
Okay. But they don't completely just collapse.
They don't completely just collapse, because eventually we reach something, a point where all of the atoms are close enough to each other that we can support these white dwarfs by something called electron degeneracy pressure.
Electron degeneracy pressure.
Yes. And that's when electrons get close enough to each other that they don't like occupying the same space, so they'll push back against each other.
They don't like occupying the same space.
They don't. It's just a fundamental nature of electrons.
So it's sort of like, so this is actually a much deeper thing. It's a quantum mechanical effect that electrons don't want to get too close to each other.
I told you, Astro has everything.
Astro has everything.
Yeah.
It's true. So it's the same thing that, for example, in an atom that keeps all of the electrons from occupying the same orbital.
Right.
They don't want to be in the same space, at the same level as each other.
So it's not quite the same thing, but you can almost think of it as like trying to push together two of the same sides of a magnet, right? They're going to push back.
Right, but magnetism is a more conventional force that we don't think
These
of.
These are fundamental particles.
Right. These are fundamental particles that are that they just can't occupy the same space. So quantum mechanics.
Right, and
purely creates a force that just keeps the star. You don't need any like. It can be as cold as you want. You don't need any thermal
Mind-blowingly,
pressure.
all it is this quantum fact that electrons repel each other.
Okay.
And that's supporting the pressure that's fighting gravity in these white dwarfs.
So this white dwarf star could be as cold as you want. It can cool down, be really, really cold, but it still won't.
If they're rising from single stars like our sun, they will just cool off ad infinitum forever.
Forever. So it's sort of like that's where stars go to retire.
Yeah.
Okay. So now, all right. So that explained a white dwarf. This type of explosion is an explosion of a white dwarf star.
Right.
Or white dwarf, if you don't want to call it a star. But it's a particular way of exploding it.
Right. So white dwarfs, we know that they can explode if they exist with a companion star, so what we call a binary system.
Okay.
And typically we think of white dwarfs explosions because we think that they're the source of type 1a supernovae.
Okay. So type 1a supernovae are, so there's a particular type of supernova.
Right.
First of all, there's different types of supernovae.
There are.
So type 1a is one example of a type of supernova,
Yes.
and it's an exploded white dwarf
Explosion
star.
of a white dwarf. But we theorists argue about exactly the details beyond that, how a white dwarf explodes, at what mass, etc.
Okay.
And so that's the problem that I studied in my thesis was details of how these 1As could be exploding.
You were saying that white dwarfs can explode by this thing called a type 1a supernova.
Yes.
And let's explain what that is. Or let's explain what the standard picture of a type 1a supernova is.
Okay. So historically, we thought that type 1a supernovae, because they all look very similar to each other, must be happening in similar systems. And the way we thought that this could work is it turns out that electron degeneracy pressure we were talking about only can support a white dwarf up to a point, up to a certain weight limit.
Up to a certain weight limit. So
Yes.
once it gets too massive, even quantum mechanics can't keep the star from collapsing or
Right.
from getting more.
Right. And so that weight limit, we call it the Chandrasekhar mass limit.
Chandrasekhar mass
Happens at about 1.4 solar masses, so 1.4 times the mass of the sun.
Okay, 1.4.
Yes.
So for our sun, when it makes a white dwarf, it won't be able to. It won't be too massive.
Right.
It's going to be maybe this mass.
Well,
of the sun,
it has to be less than the mass
It'll
of the
be
sun.
less than the mass of the sun. So maybe the sun will lose some of its envelope and leave behind a white dwarf, and that will be less than 1.4 solar masses.
So it's good. It can be a white dwarf.
So it can
stay
support
itself.
forever. It can be supported.
Right. But if it had a binary companion, we can have a process called binary accretion, where that white dwarf starts to take some of the mass from its companion and start to grow in mass.
Okay, so the companion can donate mass to the other star.
Yes.
And
so if it donates too much mass, you can reach this weight limit.
okay, so then it can get up to 1.4
Right.
times
And
the mass of
so-
the sun, the Chandrasekhar mass limit.
Right. So originally we thought that type 1a supernovae happened when these white dwarfs reach around that mass limit and they can't support themselves via this electron degeneracy pressure anymore and they explode.
Okay. This gets to a different question I had, which is normally, this is a common thing people say, is that a star can no longer support itself and it collapses, and then you get a supernova.
Right.
But that's a little weird because a collapse we think of as an implosion. So how do you get an explosion from that?
At that point, the inside starts getting hot.
It gets hot. So
It's getting hot.
So it doesn't completely collapse. It doesn't just completely fall, but it does
Starts getting hot. It starts undergoing burning processes, and there's a number of ways that can trigger slow-scale burning process into being a thermonuclear explosion.
Okay.
So that's what we put in our textbooks. That's what we teach students as the source of type 1a supernovae. But over the years, we've had trouble explaining the full breadth of this type of supernovae with that model.
Okay. So what do you mean by that? In other words, this model can, if you were to do that on your computer, if you were to explode a white dwarf star at the Chandrasekhar mass, you could get something that looks like a type 1a?
You could, but you'd have trouble getting something that looks like every type of type 1a that we see.
I see.
So there is some variation in what we see in the sky.
I see. So that's an interesting point because Sort of makes sense, because if they're always exploding at exactly the same mass, you can imagine it can be tricky to get the amount of diversity we see.
So traditionally, we looked at that one way of blowing up white dwarfs because we thought, if there is this tight relationship, then they must all be very similar explosions.
Okay, and so then it makes sense that they all exploded exactly 1.4 solar masses.
Right, exactly. However, over time, and a lot of this is to do with the fact that technology and telescopes have improved such that we've observed a lot more Type 1a supernovae, there seems to be a lot more variation than we had initially hoped. Mm-hmm. And it's a lot harder to standardize these candles than we initially thought.
Okay.
And that opened the door to, well, maybe then there's more than one way that these explode.
Okay. So then maybe that's not, maybe that picture is not always complete. Maybe sometimes they explode that way, but maybe there are other ways to explode a white dwarf star.
Right. Or at least I hope so. I think so. And I think the field at this point mostly agrees that there's probably more than one way to explode a white dwarf to get something that looks like a Type 1a supernova.
Okay, so then to summarize, Type 1a supernovae are generally I guess the general consensus is that it is an exploded white dwarf star, but the exact way you explode it might be different, and maybe some people disagree about how many of them explode by a particular mechanism.
Right, exactly. So what I studied was a way of exploding these white dwarfs before they reach that mass limit that they can't move past.
Okay, so they haven't reached the Chandrasekhar mass, but they still explode somehow.
Correct.
Okay, so how does that work?
Through something we call a double detonation mechanism.
Okay.
And this idea is not new. This idea was first proposed in the 1980s, kind of at the same time in Japan by Ken Emoto and in the US by Stan Woosley. And the idea is, if in that binary system we have a white dwarf that's eating mass from its companion, if that mass is helium,
okay,
it can form a shell of helium on the outside of the white dwarf.
Okay.
And it turns out helium's much easier to ignite than carbon or oxygen.
All right.
So you can get an initial helium detonation in that shell of accreted material.
Okay.
And then what happens is the helium burns all around the outside of the white dwarf. All right.
So hang on. I got to build the mental picture in my head. You've got a shell of helium. You have a white dwarf star, and it's made out of what? Carbon and oxygen?
Carbon and oxygen. Outside of it, kind of like a gobstopper, is a candy coating of helium.
A thin candy shell of helium on the outside, and then you set that on fire.
Right.
You
burn
set
that on fire. You detonate it.
You detonate it. So it's not just on fire. It's a thermonuclear explosion.
Right. And so that will burn starting from the initial point around the outside of the white dwarf.
Okay.
And while that's happening, it sends a shock wave from the outside of the white dwarf into the core, a spherical shock.
So now I'm picturing a ball on fire. The outside is on fire. That's the helium burning. But then you also drive a shock wave inward, sort of a spherical shock wave inward towards the center. Right.
And when that shock wave converges, it can compress and heat up enough of that carbon oxygen to ignite it and get that to detonate. So that's your second detonation.
Okay, so then you have a second detonation at the core, or near the core.
And then you get your thermonuclear runaway in a normal supernova.
Then it will look a lot more like a Type 1a because it's exploded from the center.
But we needed a creative way of doing that central detonation without reaching that mass limit that we were talking about before. Okay,
so at the time, I guess when you were talking about Stan Woosley and Ken Emoto, this was a creative idea they had.
This was a creative idea they had, but when they worked out the process, it didn't look like that typical Type 1a supernova we're looking for.
Okay, when you say work out the process, you mean like they
modeled it.
They did a computer simulation.
They did a computer simulation of it, and it didn't look like a Type 1a supernova, so we kind of benched it.
This was in the 80s?
This was in the 80s, and it turns out the problem was two things. Mostly technology. So there's a little bit of a technological issue of the computer resolution that we could have at the time.
Right.
And there was a second issue with we were missing a little bit of information about the nuclear physics. But together that meant that they could only get this system to work, this second detonation to work, if we started with a very large amount of helium on the surface of the white dwarf.
I see. So what's wrong with that? You have this big, really big shell of helium, and it blows up the star just fine.
As you might imagine, that burnt layer of helium on the outside of the ejecta leaves a visual imprint on the supernova that would happen.
Okay.
It creates some radioactive material that releases some photons earlier than we'd expect if it weren't there. And it's also like a cloud of ash that blocks some of the light coming from the inner explosion from reaching us.
Okay, so when you think, let me just to see, you have this supernova that's gone off by burning this on the outside has this these helium ashes, all this burnt helium on the outside, and then it explodes. The whole thing flies outward, and the burnt helium is still on the outside. And then when we look at it, you need this extra step where we figure out what the light looks like.
Right.
The light has to go through this helium ash.
And it turns out very quickly in the 80s we could say, that's going to cause a feature that we don't see in Type 1a supernova.
Okay, so it doesn't look like a Type 1a. It's this very distinct.
Type 1a.
Okay, we could tell that it wouldn't look like a Type 1a.
Right. So the problem was kind of set aside for a while.
Okay.
But then in the mid-2000s, the problem was picked up again because a group at Santa Barbara, so Lars Bildsten and Ken Shen, said, hey, but there's this other burning process, this other way, this other step that we were missing in understanding how the nuclear physics works of helium burning, that along with the ability to have the computational needs of a higher resolution, so a more detailed calculation, meant that you could get this double detonation mechanism to happen with not a lot of helium on the surface of the white dwarf. So that was the status of the field when I stepped in. It looked like this could be some Type 1a supernovae. It could, if there's small enough helium on the surface, a large amount of helium just doesn't look like a Type 1a. And so my thesis was re-examining this problem in detail.
Okay.
But how much helium is allowed to be there before it stops looking like a Type 1a supernova? And because I was interested in the problem of these stars exploding less than I was about only Type 1a supernovae, also, what would it look like if there was a lot of helium on the surface? Okay,
so you were just looking at it, like you said earlier, from an experimental point of view.
Right.
You're just saying, you weren't trying to get a Type 1a specifically.
No, I had two variables in my project that I wanted to tune, and that was what happens when I change the mass of the white dwarf, and what happens if I change the amount of helium on the surface of it.
And so you were just looking at it from a purely agnostic perspective of just what would happen.
Right.
And then after the fact, you can ask whether we see it in nature. But,
right.
But for the moment, you just said, okay, this is what it would look like if this exploded.
Right. And my results agreed with people who came before me that there is a space with a small amount of helium on the surface that do look like Type 1a supernovae as we think of the normal ones. But I think what has been more impactful was that region beyond what we thought could explain the normal supernovae, that area with a large amount of helium on the surface, so much that we knew this doesn't look like the supernovae we know and love.
Right. So these were the models that the thick helium shells. These were the models that were already shelved a long time ago. They were basically we did
it's not a Type 1a supernova. We're done with it.
So why bother? But you were saying, well, there's no reason these shouldn't exist.
Right. We know that the binary systems that would create this system exist in nature. We've seen them.
Right.
So if a double detonation can work to explode a white dwarf, we should see those too.
Okay. So you were saying, why not just run them, see what they look like?
Right.
And let's do a good job of it. Make sure we're using all of the all of our modern technology and doing this really precisely to make a very clear prediction. This is what exactly it would look like.
Right. And so we predicted what that would look like in detail. And
so these are the thick helium shells. So just to clarify, just to get back into context, you had done the thin helium shells, and they looked like regular
they
Type 1As.
do look like regular Type 1A supernovae.
So that's different from these Chandrasekhar mass explosions, which also look like Type 1A supernovae.
Right. And I think the field is now arguing over how many Type 1A supernovae come from which channel.
Right. But then, so now the thick helium shells.
Right.
These ones don't look like Type 1As.
They don't look like Type 1A supernovae, and at the time that I was modeling them, they didn't look like anything we had seen before. But as I said, we're living in a really exciting time of supernovae discovery.
Yes.
So around 2018, I went to a conference and gave a talk on my work and what I was working on, and included the thick helium shells. Even though they're not Type 1A supernovae, so not everybody cares about them.
But you still said this is what it would look like.
And afterwards, a graduate student from Caltech, Kishle Day, came up to me and he says, I have an object you need to see.
Okay.
And he showed me observations of a supernova that had just gone off that looked exactly what we would expect from a thick helium shell.
So it looked exactly like what you had already just shown.
What I just showed in my talk. Pretty astoundingly just like it. So we spent all afternoon comparing models, figuring out what we needed to do, where in that grid of white dwarf masses and helium shell masses, we would have to run a custom model for this event. But by the end of the day, I was fully convinced that this is what we were seeing. We were seeing...
It was just unambiguous.
Unambiguous. And to date, this is the most direct evidence we have that there is more than one way of exploding a white dwarf, that this double detonation mechanism can and does explode white dwarfs. Because to date, there is no competing theory that can create something that looks like this supernova.
I see. So what you're saying is there certainly could be different things that make the regular 1As, but for certain we know that this,
these oddballs.
This is not really. It's too unambiguous that it's not even debated what that your models make these thick helium shelves are what make. But by the way, this particular type that Kishle detected. Have there been others? There have been.
There have been a handful of others, and now we call them after this first initial one, which was 2018 BYG. So they're 18 BYG like supernovae, because we're great at naming things.
Okay, so the supernova he showed you was called 2018 BYG.
Yep.
And you remembered that well. You remember the letters.
When I started this field, so we name supernovae every year. We start with, so the first one this year was 2023A, and then
you keep going
down the alphabet, and then we go AA, AB, and I think we're in the U's right now currently as we're recording this in October. And at the beginning of my process learning supernovae and becoming a supernova scientist, I thought people who could keep track of these things were insane. And
but now
I'm one of them.
You're one of them. You remember all the letters. But anyway, 2018 BYG you'll remember forever, because that was the one that matched your predictions. That was the one that matched
our predictions.
So and there's been what you said, like 6 or
approximately 6, yeah, a handful more of them that now look like this, and it's really lent a lot of credence in believing that this mechanism can explode a white dwarf. Therefore, we should really pay attention to the subtler ones with only a little bit of helium on the surface.
Okay, so right, if a thick shell of helium can explode a white dwarf, then presumably the thin shell ones may also happen, and they may be an explanation for at least some Type 1As that we see, if not most, but we don't know the ratio.
We don't. I think the most recent estimate I read of how it was something from 30 to 60% of Type 1A supernovae. But if you ask some people, they'll say it's all of them. If you ask some people, they'll say it's none of them. We're still arguing about these details.
Right. And people like their models. And,
of course.
And that's going to be debated for a while. But but it's, the amazing thing is, we very rarely get this in astrophysics where you predict something and then we see it.
Normally we see something weird and we all race to explain it.
Right, and then you argue over what it could have been.
Yeah.
But if you already made the prediction and it was really specific, the actual, when you looked at the spectrum and exactly you could see
Right.
the parts of it where the ash was blocking the
and at the time,
radiation.
I wouldn't have bet on us discovering them because they're a little less bright than a typical supernova, but not a lot. So if they happened frequently,
right,
we would know.
Right.
It turns out we have found a few in archival data that we just didn't know what to do with.
Right, it was considered an oddball.
Right.
And we didn't know what to
and
do with
also another effect that I wasn't taking into account is they look the most different from a normal type 1 a supernova very early on.
Okay.
And so it's only really been in this modern era that we've caught them so soon after because they start off very dim and they grow brighter and then they get dim again.
Right.
But technological advancements with things like supernova cadence and just how faint we can see things have allowed us to start catching them much, much earlier.
So when you catch them at early times,
we're more likely to see the weirdness.
You're more likely to see some of this behavior that only happens at very early times.
Right.
And so it could be that there's some that they caught, they caught at peak or something.
Right, that are either less extreme.
Right.
Or in terms of how much helium was on their surface or just...
but presumably, if we've only even given all of that, if we've still only seen 6, then that does mean they're still pretty rare.
Compared to some things, but not compared to others. Compared to type 1a supernovae, sure.
Right.
Compared to other transients, 6 since 2018 is not so bad.
Okay, that's fair. There's some things that are much rarer than that. So what is next on the horizon for you? What are the next big questions to tackle?
Well, on a simpler term, I just started a faculty position. So next is figuring out how that works. So,
okay.
But science-wise, again, I'm just sitting here trying to be ready for the incredibly rich discovery space we're about to embark into. As you said, JWST just launched. We're starting to learn from that what happens at the very center of supernova explosions and things like how they interact with their surrounding dusty environments. We're about to start the LSST at the Vera Rubin Observatory. We have a number of other big telescopes and big satellites planned for the next decade or so. And all of that will give us things we hadn't been able to look into before and things we hadn't even dreamed of.
Yeah, I mean, that's what a lot of astrophysics is. You kind of, we're kind of betting on that if you point your telescope at something or you look in a way that we haven't been able to look before, you're just going to find things. And we usually win that bet when we do that. We usually discover things we didn't expect.
Absolutely. I think for me, in this new era, what I'm most excited about is being able to couple signatures that we see from those gravitational waves we talked about briefly earlier with photons that we're seeing from astrophysical transients and simultaneously learn about the mass of the system from the gravitational waves and things it leaves behind, like black holes, with, the explosion physics themselves that we get to see from the photons.
That is very exciting that we're now able to, do things to actually directly observe black holes, and what they're doing. We're actually seeing things. Not only are we looking at them with the Event Horizon Telescope, but we're also being able to actually see black holes merging with LIGO, and those are very big developments, and I'm sure that's going to just...
you could have more than one episode of this podcast devoted to just that.
Yeah, of course, absolutely. All right. Well, thank you so much, Dr. Polin, for indulging us with your wisdom.
Thanks again for having me here.
I had a lot of fun talking science with you. I hope you will join us again sometime.
I'm sure I will.
Well, that was quite an interview. It gives you a sense of how exciting it can be to be a scientist and have one of your predictions actually come true. Well, hopefully I can keep finding impressive astrophysicists to talk to, maybe once a month. We'll see how I do. Thank you so much, Professor Polin, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206299. The music that you're listening to right now was written and recorded by Britton Ashford from her album Trotter. All songs are used with permission from the artist and producer. Look her up if you enjoyed it. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, Professor of Physics and Astronomy at Purdue University.